So let's now briefly discuss Chapter 10, potentials, gauges, and how they relate to the electromagnetic fields that we have. Okay, so I just wrote a few equations to get started quickly. First of all, Maxwell's equations in vacuum in the presence of charge density and current density source fields. Okay, and Maxwell's equations are written in the form of having all the fields on the left-hand side and all the sources on the right-hand side. Now, the whole point of electrodynamics, as you know by now, is that if I give you the source rho and j, you should find the e's and the b's. In the general case, however, I'm sure you can see that this is quite a tough contract. Okay, as we've seen before, of course, the rho and the j have to fulfill the continuity equation, so it's not like you can put anything in there. But still, in a generic case, it's quite tough. So one of the simplification strategies that you can have is to rewrite your fields in terms of potentials. Okay, so let's just discuss that very briefly. You'll remember we have scalar and vector potentials. Okay, potentials. So how does this work? Okay, because the divergence of B is equal to 0, it means that automatically we can write B as the curl of some other object. Okay, and this A is the vector potential that you've seen. Okay, vector potential. Okay, and we did a lot in statics for all these things, electrostatics, magnetostatics, but now we're going to do it for the full electrodynamics case. Okay, if we put this in Faraday's law, then what we get, we get that, you see, Faraday's law tells us that curl of E plus dB dt is equal to 0, so I can just substitute this in there, take the curl out. Okay, it tells me that the curl of the following quantity, E plus dA dt, is equal to 0. But if the curl of something is equal to 0, it means that we can write it as the gradient of something else. So we can write that E plus dA dt is the gradient of something else. And then by choice, we say that this something else is minus V, okay? So grad V minus dA dt. So even in the dynamic case, the electric field is fully determined by the scalar and the vector potential. Okay, so that's a thing. And now, please understand, right, that the use of this representation automatically fulfills the two homogeneous Maxwell equations, right? That that these two equations here, so Faraday and then also this no-name equation, are automatically fulfilled just by choosing this representation for the B's and for the magnetic field and for the electric field. Okay, so now our job consists into looking at the inhomogeneous Maxwell equations. Okay, so if I substitute this into Gauss, okay, then what does it tell me? So I would need to take the divergence of this, so I would get now minus, let me take care of the minus sign. So I would take that the Laplacian acting on V plus the time derivative of the divergence of A would be equal to, with a minus sign, what we had on the right-hand side of Gauss's law, rho over epsilon 0. Okay, so that's that's one of the equations that remains. So if we do that in Ampere Maxwell, so the other inhomogeneous equation that we have, then I want to look at the yeah, so I just want to look at the curl of all of this. So I want to do the following thing. I would say that the curl of A, okay, is equal to now mu 0 j, okay, minus mu 0 epsilon 0, the gradient of dv dt, minus mu 0 epsilon 0, now the second derivative of A with respect to t squared. Okay, and now, as usual, we can use the trick. There's a vector identity that tells us that the curl of something is the gradient of the divergence of that something minus the Laplacian of that something. So finally, what we get is the following thing. So this whole thing here becomes that the Laplacian acting on A minus then so I'm just taking care of my sign. This comes on the other side here. Mu 0 epsilon 0 d2A dt squared minus the gradient of another quantity. So I had the divergence of A, and now this this bit here. So plus mu 0 epsilon 0 dv dt. This whole thing has to be equal to this this thing, but now with an extra minus sign, just by convenience, mu 0 j. Okay, so this is these are the two leftover inhomogeneous Maxwell equations that we have, and they're not very pretty. They're a bit unhandy to play with, but nonetheless, they are what is left over of the set of 4 Maxwell equations that we had to deal with. Okay, so there's nothing else. Now, to discuss the solution of these things, there's one handy thing that we can use. So this handy thing is that there is a redundancy in the representation for the electromagnetic fields in terms of the potentials. And this redundancy is called essentially, if you want, a gauge redundancy. So we can talk very briefly about gauge transformations. Now, the observation is that the E and the B fields, and again, I'm repeating things that you already know, they are invariant under change of V and A potentials. Okay, so if I redefine my potentials in the following way, I have a V prime, which I define as V minus some time differential of some function, and then A prime, which is A plus the gradient of this function. Okay, and for any function lambda of RT, then if I just substitute these transformations inside the expressions for the fields, I get the same thing, because you see, so in the expression for E, I have these two terms, grad with d dt of A, and these two things cancel, right? Because I would take grad of this and then d dt of this, and these two things would add up to 0. And if I just look at this one here, if I take the curl of this to represent my b, then because this is already a gradient of a function, its curl automatically vanishes. So that's the way to do a gauge transformation. But what does that mean? It means actually that by judiciously choosing our lambda, we can set some of these functions to 0, or some combinations of these functions to 0. Okay, so we can discuss two examples of gauge choices. So here's a first gauge choice, number 1, the Coulomb gauge. And here, what we do is that we say that the divergence of A is equal to 0. So why is that simple? Then the first inhomogeneous equation that we had simply becomes the Poisson equation. Okay? And the solution for this, we already know. The solution for this is the following. Integral over the whole volume of the charge distribution at r prime and t divided by r minus r prime. Okay? So this is kind of a funny thing, because although the solution is explicit, it's a single time equation. It's an equal time condition. So irrespective of the distance between the evaluation point and the source point, then the scalar potential is given by this. Now, you don't have to worry too much, because that doesn't mean that information is traveling faster than light. This is just a representation. The value of the actual scalar potential itself is not physical. What is physical is the combination of it with the vector potential to give the electromagnetic fields. Nonetheless, this is kind of a handy way of writing a solution. So Gauss looks very simple in this gauge choice. But the bad news is, of course, pushed into the equation for the vector potential. So if I look at Ampère-Maxwell, then it becomes Laplacian of A minus mu 0 epsilon 0 second derivative of A with respect to t is equal to minus mu 0 j. But then, yeah, so this this other term here that ruins the party, grad of dv dt. Okay, so so this extra source term in there makes it quite difficult to find a solution for all of this. Okay, so so then let's do something else. Let's do gauge choice number 2, the Lorenz gauge. And here, what we do is that we choose a more complicated combination to vanish. You see, in the Ampère-Maxwell law here, there was this annoying term here. So why don't we just set this whole thing to 0? That's the choice that Lorenz made. You choose that the divergence of A plus mu 0 epsilon 0 dv dt is equal to 0. And in that case, things start looking quite aesthetic. Because if I look at what happens to Gauss's law, okay, then I already had what we had above, mu 0 epsilon 0 d2v dt2 is equal to minus rho over epsilon 0. But now if I look at Ampere Maxwell in this thing here, you see what I'm left of Ampere Maxwell is just this, but this term is now just gone. Okay, so if we just rewrite this cleanly, it just means that the Laplacian of A component-wise minus mu 0 epsilon 0 d2A dt squared is equal to minus mu 0j. Now the really cool thing is that these equations now are on the same footing. Very, very similar. Yeah? So for the scalar potential, you are sourced by the charge density distribution. For the components of the vector potential, you're sourced by the components of the current density that you have. Okay, so this is kind of the most aesthetic way that we have of rewriting these things. Now, we can just use some simple notations here. Notation. We can define an operator, which is little square squared, which is by definition the Laplacian minus mu 0 epsilon 0 second derivative with respect to time. And this is called the D'Alembertian. Okay, so D'Alembert. That leads to Maxwell equations in Lorenz gauge, which are just that the D'Alembertian on V is equal to minus rho over epsilon 0, and the D'Alembertian on A is just equal to minus mu 0j. Okay? This is the most compact and aesthetic version of Maxwell's equations. Of course, they're the same equations. We haven't dropped any content, we haven't added any content. It's just a nice way to represent it. Okay? So these are really the equations that typically you'll want to play with in relativistic theory and things like that. So we'll get back to those a bit later. Okay, so that's it. The rest of chapter 10 I will actually leave out in view of time. So I just want you to be familiar with this representation of the electromagnetic fields in terms of scalar and vector potentials, generalized to the fully dynamical case as compared to what we did before.